Hello, everyone. Welcome to the class of electronic devices. So this is lecture number 5. We are covering chapter number 1 of the book. So we have been talking about these amplifiers. In the last lecture, we modeled an amplifier, developed its equivalent electrical model of an amplifier. We saw its terminal characteristics. By now we have discussed how to find the voltage gain, current gain, and the power gains of the amplifiers. So today we are going to do another example problem that would further help to solidify some of the concepts. And then we will also do a quick analysis of current amplifier, transconductance, and transimpedance amplifiers as well in this lecture. Okay, so let's start with an example. I already drew this circuit, so that would save time for the lecture. Now, if you look at this example, this is an example of a cascaded amplifier in which multiple amplifiers are connected to each other. And if you look closely, then this is one amplifier. This is the second amplifier, and this is the third amplifier, or we can also call it as stage 1, stage 2, stage 3. So these are the 3 different stages of an amplifier which are connected to each other in a cascaded way, right? So this is an example of cascaded amplifier example. Also note down a few other things. We have these 3 amplifiers. If you look closely, the internal structure or the internal schematic of the amplifiers is exactly the same. We have input impedance. Over here, this is the input impedance of the amplifier. This is the input impedance for the second stage, input impedance for the third stage, output impedance of the first stage, output impedance of the second stage, output impedance of the third stage. And then similarly, we have the third component was a voltage control voltage source. For the first stage, it is 10 with this as a gain factor. This is for the second stage with 100 as a gain factor, third stage with a unity gain. And then we have a source voltage that is attached that we want to amplify using this cascaded structure. We have a source resistance, 100 kilo ohms over here. And now this entire thing is connected to a load with a 100 ohms value. Okay, so what we want to do in this example is we want to find out the voltage gains. We want to find voltage, current, and power gain. That's right. So we want to find out the voltage gain, current gain, and the power gain of these amplifiers of this cascaded amplifier. We also want to find out the overall voltage gain as well. Overall voltage gain. And if you remember, we discussed the difference. What is the voltage gain of an amplifier, which is the output voltage to the input voltage drop at the amplifier, right? So in this case, it will be the output voltage across the load to the VI1. And the overall voltage gain, that is going to be the output voltage to the source voltage. So we're gonna do this in more detail. Okay, so let's solve this problem. Solution. So the easiest way to solve this is, let me write these things down. All the resistance value, that is going to help us solve this quicker. So we have 3 stages of an amplifier. Okay, so we have first stage, second, third stage. And then our values are, we have a source resistance, an input resistance, an output resistance, a load resistance. We have an AV naught, and then we need to find out the value of AV. All right, so for the first stage of an amplifier, let's look at the first stage now. The value of the source resistance is 100 kilo ohms. The value of the input resistance is 1 mega ohms. The value of the output resistance is this one, 1 kilo ohms. The value of the load resistance that will serve as a load for the first stage will be this resistance, 100 kilo ohms. Yeah, I'm going to stop writing this symbol, I think. All right, similarly, let's do it for the second stage. For the second stage, the source resistance is 1 kilo, input resistance is... Okay, for the second stage, sorry, the source resistance is 1 kilo, the input is 100 kilo, the output is 1 kilo, the load is 10 kilo. For the third stage, our source is 1 kilo, input is 10 kilo, output is 10 ohms, and finally the load resistance is 100 ohms. All right. Right, just assume the ohm symbol at all of these values as well. All right, now let's find out, the values. Let's also write down the voltage gain AV naught values. So the AV naught for the first stage is 10, for the second stage is 100, for the third stage is 1. So it's 10, 100, and 1. All right, so this so this will simplify us while finding out these values. So if you remember, the formula for the voltage gain is, what is the formula for the voltage gain? We have AV naught into RL over RL plus R naught. Right, okay. And this is essentially, all right. So when we put down these values over here for the first stage, right, if I have to calculate AV1, for the first stage, AV1 is equals to AV naught, 10 multiplied by RL, 100K over RL plus R naught, 101K. The answer will be equals to, 9.9. Similarly, when we do AV2, put down all the values, 100 into 10K divided by 11K, the answer is going to come out to be 90.9. And similarly, when you do AV3, the answer will come out to be 100 over 110.909. So these are the values of the gains of the 3 stages of the amplifiers. So what is the value of the total voltage gain? Again, this is not the overall voltage gain with respect to the source. This is the voltage gain of this cascaded stages of the amplifier. So the total voltage gain of these cascaded stages will be, so essentially it is equals to the load voltage to the VI1, the first one. It will be the product AV1, AV2, AV3. So 9.9, 90.9.909. It will come out to be 818 volts or volts. You can also convert that using 20 log of 818 into, so the value in dBs, that will come out to be 58.3 dBs. Again, this, for example, this is coming out from here, 20 log of 818. So this is the value of the voltage gain of an amplifier. All right, so before we move to the current gain of an amplifier, we can also, let's first find out the overall voltage gain of an amplifier. All right, so what is the overall voltage gain of an amplifier? That was the second thing that we want to determine. Overall voltage gain. Again, when we say this word overall voltage gain, this means that what we want to do is we want to find the output voltage, VL or V naught, divided by the source. So the overall voltage gain of the amplifier is the gain of an amplifier with respect to the source voltage that we want to amplify. we can convert that into VI1 multiplied by VI1 divided by the source. We already know the value of VL over VI1 from this one. We just calculated the value VL over VI1, which is 818. The other value that we want to determine is VI1 over VS, which is essentially coming from here. If you apply a voltage divider rule over here, you can easily find out this value. So VI1 over here, VI1 equals VS. If you apply a voltage divider rule over here, right? So it will be VS multiplied by 1 mega over 1 mega plus 100K. So I'm going to apply, in order to find out the value of VI1 over VS, I'm going to apply a voltage divider rule there. And when we apply a voltage divider rule there, we get 1 mega over 1 mega ohms plus 100K. The answer will come out to be 0.909 when you solve it. So you can replace the two values here. So this value can come over here. The value of VL over VI1 is, going back to over here, 818. 818 multiplied by 0.909. The value that we got will be 743.6 volts per volts. All right, so this is the overall voltage gain of an amplifier. All right, so the next thing that we want to determine is the current gain of an amplifier. Current gain. In order to determine the current gain, we discussed the formulas earlier for the current gain. Current gain is AI, which is equals to I naught over II. So let's look at what is I naught and what is II in our circuit. Right, so our I naught is over here. So I naught can be written as, if we have been using this as VL. So I naught will be VL over here divided by the load resistance, which is 100 ohms. And similarly, the input current over here, II, is equals to VI1 divided by 1 mega ohms. So using these two, I can easily calculate it. So it will be VL over 100 ohms divided by VI1 divided by 1 mega ohms. I already know again the value of this VL over, so this can be rewritten as VL over VI1 multiplied by 1 mega ohms over 100 ohms. Right, so VL over VI1, we already know the value, 818. So it will come out to be 818 multiplied by 10 to the 6 divided by 100, 10 to the 4. So the answer for the AI will come out to be 8.18 into 10 to the 6 amperes. And if you will convert that into the log or the decibels, the gain will come out to be 138.3 dBs. This is the value of the current gain. Now the power gain is a pretty simple. We have been doing that in the past. The power gain, AP, is simply the product of the voltage gain and the current gain. So the product of the voltage gain is 818 over here. And the current gain is 8.18 into 10 to the 6. The value that we will get is 66.9 into 10 to the 8 watts per watts. Again, it's power, the units are watts. And if you convert that, again, the formula for in expressing the power gain in decibel is 10 log of power gain, the modulus of power gain. So it is going to come out to be 98.3 decibels. Right, okay, so this is how we ended up determining all the values. Some other interesting points to look over here is, for example, if I will, in terms of the cascaded amplifier, we can look back at the cascaded amplifier and see that the first stage of the amplifier, the stage number 1 over here, has a very high input resistance that we want. However, the gain is moderate. It is still amplifying the signal 10 times. For the second stage of the amplifier, our the main amplification is happening in the second stage of the amplifier, which has a bulk of the gain, like almost 100, right? And similarly, the third stage of the amplifier has a unity gain. However, it has a very low output impedance that we need for to get a good amplifier. So we discussed the design considerations in the last lecture. So if you remember from the design considerations, we want a very high input impedance and a very low output impedance for a voltage amplifier. We will discuss other type of amplifiers in this lecture as well, and you will realize that the design conditions for a good amplifier, for a good current amplifier, transimpedance or transconductance amplifiers, the conditions may be different. For a voltage amplifier, the input resistance, input impedance of the amplifier should be very high, ideally infinite, and the output impedance should be very low, ideally 0. All right. So notes, in terms of notes, our first stage has high input impedance with moderate gain. As I just discussed, our second stage has bulk of gain. So the main signal amplification is happening in the second stage where the gain factor was 100. And for the first stage was just 10. And third stage, for the third stage that is connected to the load, of course we wanted to have a very low output impedance, so it has a low output resistance, low output resistance with unity gain. Over there we did not worry about the gain because our main signal amplification has already been happened. What we just worry about is that our output impedance should be small so that there is no potential drop over there, or very low potential drop over there. All right, so this was an example of a cascaded amplifier. So the take-home message from this example is that whenever you see this long circuit with a lot of different amplifiers that are connected to each other, this is an example of a cascaded amplifier. And the way to solve this amplifier is to divide that into different stages and then solve for each stage individually. And then the overall gains of the amplifier is going to be the product of the gains of all the stages together. Okay. So next we are going to talk about 3 other types of different amplifiers. We discussed our voltage amplifier in most detail. Now we will be quick in discussing the 3 other types, which are, the analysis is pretty simple and similar. Okay, so let's talk about our other type of an amplifier, which is current amplifier, right? So current amplifier in which we are trying to amplify the current. So I'm going to make an equivalent electrical circuit of the current amplifier, and then we're going to quickly solve it. Okay, so for a current amplifier, my input is a current rather than a voltage. So we have a source current now rather than a source voltage. So let me quickly make it. Right, so this is load resistance. Why not? All right, so this is the internal schematic of the what the current amplifier looks like. If you look now closely, what do we have over here is we have a source current, and then we have a source resistance that is connected to the input of the amplifier. The input of the amplifier is going to have an input resistance, Ri, right? And similarly, our amplifier is connected to the output, which is the load resistance. Our amplifier is going to have an output resistance represented R naught over here. And what we have over here, rather than having a voltage controlled voltage source, now what we have is a current controlled current source, right? And the gain with the gain factor of AIS, right? So this is the gain of this of this amplifier, of this amplifier. Okay, so let's quickly solve this amplifier now. If you remember from while we were solving the case for the voltage amplifiers, we kind of we find out the voltage drop at the input, and we find out the voltage drop at the output, and then we determine the gain factors. What is the voltage gain there? In this case, we are going to determine what is the current gain here, right? And similarly, we will determine what are the design considerations to make sure that we will get the maximum gain out of it. All right, so if I will look at the input stage, or the input over here, input of this amplifier, I can determine the value of II as by applying a current divider rule. So I will determine this value, and I will determine this value. So, right, because in this current amplifier, what we are trying to do is, or what our gain will be equals to, I naught over II. So this is what we are interested in. So this is what we are going to solve for. So our output current and input current. So our input current can be determined by using a current divider rule at the input. So II will be equals to the source current, IS, into RS over RS plus RI. Similarly, I naught will be equals to AIS II into R naught over R naught plus RL. All right. Now, current gain. So let's determine the current gain. What is our current gain of a loaded amplifier? Loaded amplifier means RL is connected, right? We have connected amplifier to a load resistance. So the current gain of a loaded amplifier, AI, equals to I naught over II. And I can use this equation to determine this value. AI over II is equals to AIS into R naught over R naught plus RL. This is the value of the current gain for a loaded amplifier. Now, interestingly, if we see that if over here our load resistance is 0, which means that it's a short circuit, right? Short circuit, our AI will become equals to AIS. So that is why this AIS is known as short circuit current gain. I hope that this is in contrast to the open circuit voltage gain of a voltage amplifier, where we wanted to have our load resistance to be infinite or an open circuit. So that is why for a voltage amplifier, that was called as an open circuit voltage gain. Over here, when the load resistance is 0, our current gain of a amplifier will become equals to the value of AIS. So that is why AIS is known as a short circuit current gain. I hope you will remember the difference. Okay, in terms of design or conditions of a good amplifier. All right. So the first condition of a good amplifier is what we want is we want our input resistance, right? We want our input resistance to be very, very smaller than the source resistance. Input resistance to be very, very smaller than the source resistance. When we will make our input resistance very, very smaller than the source resistance, this will enable us that we will not lose any current in the source resistance branch, and most of the current will come to the input state of an amplifier. And our second condition will be that our output resistance R naught should be as high as possible so that all the current will flow through the load. So R naught will be equals to infinite, which means that R naught should be exceptionally larger than the load resistance. Now you can also see that both of these conditions are in contrast to the voltage amplifier, where for a voltage amplifier we wanted to have our input resistance to be infinite and output resistance to be very small or zero. Over here for a current amplifier, our input resistance should be very smaller than the source resistance and our output resistance should be very high than a load resistance. Okay. Now, very quickly, we are going to discuss another type of an amplifier known as a transconductance amplifier. Transconductance amplifier. So let me draw the circuit. In a transconductance amplifier, we will have a voltage source that we want to amplify, and then this will draw the current II. Our input impedance of the amplifier will be Ri, and the potential drop across it will be Vi. Right? Then what we will do is we are going to have a transconductance amplifier where so rather than having a current controlled current source or a voltage controlled voltage source, over here we have a voltage controlled current source, right? So this is a current source and this is controlled by the voltage Vi. And this is our output impedance of the amplifier, and this output impedance is connected to the load resistance RL. The potential drop across will be R naught and the current will be I naught. So this is how our transconductance amplifier looks like. So similarly, we are going to very quickly solve the equations. So the important thing over here, again, the gain, what we ideally wanted to determine. So solving all of these amplifier circuits over here, what we want to do is we want to determine the gain, right? So the gain of a transconductance amplifier is our output is a current, input is a voltage. So what we want to determine is I naught over Vs or Vi. For an overall voltage gain, it will be I naught over Vs. Okay. So in order to determine I naught and Vi, all we need to do is to apply a current divider rule at the output and a voltage divider rule at the input, right? So if I will apply a voltage divider rule at the input voltage Vi will be equals to Vs into Ri over Ri plus Rs. Similarly, if I apply a current divider rule at the output, my I naught would be equals to GMVI into R naught over R naught plus RL. So the gain that we will get out of it will be equals to, so the gain I naught over Vi, right? So this Vi can go over there, will become equals to GM into R naught over R naught plus RL. This is how we can determine the gain of a transconductance amplifier. Now design characteristics, design conditions again in terms of resistances and the voltages. Right, since our input is a voltage source, right? So we can have our first conditions to be similar as for a voltage amplifier, in which what we want is we want our input resistance to be sufficiently larger than the source resistance, or ideally we want our input resistance to be infinite. And second, since we have a current output or at the output, so what we want is our output resistance should also be very, very larger than the load resistance. So we want our output should be also very equals to infinity, also similar to the current amplifier over here. So this is how we can analyze a transconductance amplifier and find out its conditions. We have one more amplifier left that we can quickly do it, and before we wrap up our lecture today. So our last amplifier that we will discuss today is a trans-resistance amplifier. Trans-resistance amplifier. So in a trans-resistance amplifier, we have a current source. So this is a source resistance that will appear in parallel to this. Then we are going to have a input resistance of an amplifier. The current that is drawn from the source will be II. Then we are going to have a current controlled voltage source, output resistance R0, load resistance RL, and a potential drop across V0. So what this will, let me connect over here. This is the ground, and here is your model of an amplifier, of a trans-resistance amplifier, right? The gain of the trans-resistance is over here denoted by Rm. Okay. No, so what we want to find out, the gain of this trans-resistance amplifier is going to look like our output is V0 and our input is Is. Or over here we are determining II. If for an overall voltage gain, for an overall gain of the trans-resistance amplifier or overall trans-resistance gain, it would have been V0 over Is, which we can easily determine as well. Okay. So in order to find V0, we can apply a voltage divider rule at the output. In order to determine II, we can apply a current divider rule at the input. So let's determine both of this, starting with, I'm going to apply the current divider rule at the input. So II will be equals to Is into Rs over Rs plus Ri. Similarly, we can apply a voltage divider rule at the output. V0 equals to RMVI into RL over RL plus R0, right? So our gain, or our trans-resistance gain, so our gain will become equals to RM RL over RL plus R0. So this will become a gain, a trans-resistance gain of the gain of the trans-resistance amplifier. This is not the overall trans-resistance gain, because in that case we need to determine our overall gain would have been equals to V0 over Is, right? And we can easily determine that using our first equation. We have done that in the past many times. Okay, and finally our design conditions, right? If we look closer, our input looks like a current amplifier, so design condition will be the same over here, that our input resistance should be ideally 0, or our input resistance should be very, very smaller than the source resistance. And our second looks like our output over here looks like a voltage amplifier, so condition will remain the same, where our output resistance should also be ideally 0, or our output resistance should be very, very smaller than the load resistance. All right, so this is the trans resistance amplifier. This was the last topic that we want to talk about today. And in the next lecture, we are going to start talking about the frequency response. Again, what we have discussed in this lecture, we started with the cascaded amplifier. We talked about that we can connect these multiple stages of an amplifier, and each stage can have its own unique purpose. The stage 1 over here provides a moderate and okay gain, but the main objective of that stage was to provide a very high input impedance. The stage 2 was doing majorly the amplification over here with a 100 gain, and the stage 3 was providing a very low output impedance for the voltage gain. And in order to determine the voltage gain of this cascaded amplifiers of all the stages together, we can consider one state at a time, find out the gain values, and then multiply all of them. Similarly, then we talked about the current amplifier. We solve for a current amplifier what we are interested in finding I naught over II. So in order to find I naught over II, we can apply the current divider rules at the input and the output. And we then determine its conditions for a good amplifier. Similarly, for a transconductance amplifier, our gain that we are interested in is I naught over Vi. So we can apply a current divider rule at the output, a voltage divider rule at the input. And finally, the trans resistance amplifier, which is the gain for which is V naught over II. So we can apply a voltage divider rule over at the output to determine this, and a current divider rule at the input to determine this. We have also seen the design conditions for all of these amplifiers. So all of these topics are very important in terms of concepts, and some may or may not come in terms of a concept, some may or may not come in the exams as well. All right, so with that, thank you so much. This is the end of this lecture, and I will talk to you in the next lecture again. All right, thank you so much. Have a good rest of the day. Bye-bye.